Well, good morning and happy Monday. Let's move on to membrane filtration. This is the second to the last unit. We'll talk briefly. So when we talk about membrane filtration, we talk about basically four types. And those four types are reverse osmosis, nanofiltration, ultrafiltration, and microfiltration. We can think of reverse osmosis and nanofiltration as pressure driven. And we can group ultrafiltration and microfiltration as sieving. There's overlap between those two, and all of these, except microfiltration, require significant pressures, but we can essentially divide it up in that way. Now, all of these involve the use of a semi-permeable membrane. That membrane is permeable to water, and as you'll see, some other substances depending on the membrane type. And the rate of passage of water and also solvents really depend on pressure, the concentration of those solvents, those solutes in the solution, and then temperature. So pressure, concentration, and temperature are the major controlling factors, along with the properties of the membrane itself. So I'm going to do play a short video, and this demonstrates the issue or the concept of semi-permeable membranes.
One we'll use as our control. The second one, we'll put in a beaker of water. 2 hours later, let's see what our results are. You can see definite change in the volumes. And if we move this around, you can see that in this larger volume, the molasses is not nearly as viscous. So we have plenty of evidence to support the fact that the water molecules move through the dialysis tubing and it's diluted the molasses.
Okay, so this is just a shortened video. The entire video link is at the bottom of the image. Basically, what was done here was to take dialysis tubing and in that place molasses in the dialysis tubing. You see the first, the control, which is just the molasses in the dialysis tubing, and then the other showing the dialysis tubing after it sat in water for about 2 hours. So what you see is that the water the membrane is permeable to water, so it allows water to pass into the membrane. The sugar molecules aren't able to pass out of the membrane, and then what you see is that the molasses becomes more dilute. So it tries to give you a sense of what we're talking about when we're talking about semi-permeable membranes. So membrane processes are extremely effective. We'll talk about in the next couple slides. They're effective at removing a variety of contaminants depending on the type of membrane we're using. The problem is that the rate of water flow across the membrane is slow. So we need a large membrane area, and that presents some significant challenges. Now, we can use this, though, to separate colloidal and dissolved solids that we couldn't separate effectively by either sedimentation or by granular media filtration. The disadvantage is that there is a high pressure drop across the membrane surface, And that means that the system requires a high amount of energy input. This figure here shows the different types of membranes. And as I've mentioned, we have microfiltration, ultrafiltration, and nanofiltration, and then reverse osmosis. So in terms of pressure, microfiltration is operating at about, think of it at about 1 atmosphere, okay? Or less than 14.5 psi. As we decrease the pore sizes here, we increase the pressure required across the membrane surface. So we're talking here about 14 to about 150 psi. Here we're talking about 300 to 600 psi, and here 600, about 600 to, and this isn't exact, but to about 900 psi, just to give you an indication. So again, as we decrease the pore size of the membrane, we're increasing the pressure that's required. Now, in terms of removal, you see here, what we're removing is predominantly bacteria and fats. So, for example, microfiltration can be used to remove bacteria. It can also be used to remove cryptosporidium and giardia. It can also be used in some industries, for example, in the production of skim milk, because it will remove the fats from milk. We move to ultrafiltration, and now we're starting to remove proteins. We're going to remove bacteria, cryptosporidium, oocysts. Pressure is increasing, but we can remove more of the contaminants. We can also remove some viruses. Now, when we move to nanofiltration, now we're removing, again, smaller molecules. We can remove essentially all viruses. So we will remove the bacteria, we'll remove crypto, and then almost all, or essentially all, viruses. And then when we're looking at reverse osmosis, now we're looking at removing ions. So when we're looking at desalination, so removing of the salts from seawater, we're looking at reverse osmosis. We may be able to get some removal of these same ions with a tight nanofiltration. You can see there's some overlap in terms of both the pore diameter and also in terms of the pressures that are used. This is just another image to, again, show you what we're removing. So we've talked about granular media filtration. So when we're looking at, for instance, sand filtration, we're looking at removing particles in this range. We can remove algae. We can remove cysts and oocysts, so giardia and cryptosporidium. We can remove most bacteria. And in fact, we'll get some additional removal because of just attachment. When we're looking at microfiltration, we're now removing essentially all of the bacteria. To remove viruses, we need to move to ultrafiltration. We can remove organics, and this really depends on the molecular weight at tight ultrafiltration membranes. And then we're looking down at nanofiltration and reverse osmosis to remove dissolved ions. So this kind of gives you a range, both in terms of molecular weight of the compounds that we're removing, and then the pore size of these membranes. Now, when we talk about reverse osmosis, the way osmosis works is that it's the net movement by diffusion of a solvent from a region of higher water concentration to a region of lower water concentration. So you can see here, we have a higher concentration of, let's just say, sodium chloride. And then we have a lower concentration on the other side of the membrane. You saw that with the molasses experiment, except in that case, it would be sugar. So what happens? The water moves across the membrane. The ions in this case are unable to move across the membrane, so we end up with a more concentrated solution on one side and a less concentrated solution on the other. And the attempt is to show that you can see that the water level changes because water is moving across the membrane. Now, with reverse osmosis, what we attempt to do is the opposite. So we apply a pressure here. We're pushing water across the membrane. This becomes our permeate. This is what we're producing. And then what doesn't pass through the membrane becomes our reject stream. So we have two streams that we start with one. We produce a permeate stream, and this is our product stream. And then we have a reject stream that has the higher concentration of whatever we're attempting to remove. To give you an idea of the differential energy cost, here is conventional surface treatment. So this is just energy costs in kilowatt hours per cubic meter of water produced. With desalination, we're typically treating water that has about 35,000 milligrams per liter of TDS. For water reuse, we're looking typically at waters that contain about less than 1,000 milligrams per liter of TDS. Now, when we talk about water reuse, often what we're talking about is what we call intended water reuse. So we take wastewater effluent, we're passing that through ultrafiltration and RO, and we're producing water that could be used for potable water. That's the whole idea. So what is unintended water reuse? So this is unintended water reuse. We're recycling wastewater effluent and then using it for drinking water. It's used in areas where water is scarce. So you'll see it used, for instance, in Israel. Singapore recycles a portion of their wastewater effluent. So what's unintended water reuse? You have the East Lansing wastewater treatment plant. Where does the effluent go? That
Into the Red Cedar.
To the Red Cedar. And where does the Red Cedar go?
Does that go to Grand River?
Mm-hmm. And where does the Grand River go?
Lake Michigan.
Lake Michigan. And who uses Lake Michigan water for drinking water?
Some West Coast cities.
Yep.
In Michigan.
Grand Rapids, Muskegon, basically Holland, pretty much the entire west side of the state. And then Chicago, Milwaukee, anything along the the west side of Lake Michigan. That is unintended water reuse. I used to have a t-shirt that said we all live downstream. If you think about it, in effect, we all do. Anyone that's using surface water, we're recycling the water that we have in the hydrosphere. So that's unintended water reuse. Intended water reuse is when we actually plan to use the wastewater effluent for potable water. Any questions about this? So you can see in terms of cost, it's a lot more costly from an energy perspective to desalinate water than it is to reuse water. And then vapor distillations is extremely expensive, which is why we don't use vapor distillation on a large scale for water treatment. It's just orders of magnitude more costly than either conventional surface water treatment, desalination, or water reuse. Now, in terms of the cost of desalination, a significant cost is electricity. Another significant cost are consumables. This will include replacement of membranes. Typically, you're replacing polymeric membranes about every 3 to 5 years. In terms, this here is more of the actual housing for the membranes. It also includes chemical costs. As we talk about, there's often chemical pre-treatment and post-treatment that we need. Cleaning of the membranes, we'll talk about fouling. So all that would be in consumables, and then just in spare parts, investment costs. Staffing to run the plant is actually relatively small. It's only about 1%. Running the plants are not a significant cost in terms of a desalination plant. Membrane replacements, consumables such as chemicals, and electricity are your major costs. Now you'll also hear about forward osmosis. This is an attempt to get around the pressure issues or requirements on a membrane, on a regular reverse osmosis membrane. So instead of applying pressure, what they're doing is they're using a concentration gradient. So they're using a high concentration, in this case shown here, of sodium chloride. And that concentration is what's driving reverse osmosis.
Percent of dissolved impurities, but is super thin so H2O can easily pass through. Just as impressive, Oasis uses a highly concentrated salt solution to draw clean water across the membrane without using energy-hungry high-pressure pumps. The water and draw solution are then separated using low-grade heat or a secondary membrane. The draw solution returns to the system in a continuous process, leaving fresh water ready for industrial use or human consumption.
So you can see in this video, a portion of the video, is that, again, what they're doing is they're using a high concentration brine solution to create that concentration gradient in order to drive water across the membrane. You still have your reject stream. And then what they're doing is shown here is with a secondary membrane. So here, this is the reject stream from the secondary membrane. This is the product stream here. So this is the clean water that would then be used. The advantage of this is you can see kind of by the color that if you have, and what we'll talk about fouling, removal of this organic material, removal of bacteria, that would occur here. So this is the reject stream. Water passes across here, and then what we're going to do is we reconcentrate here the salts, and then we're going to use this gradient again. And it just, so essentially it's a dual loop membrane system. So in terms of the membrane system, I've mentioned the issue with pressure. When we're looking at a conventional membrane system, we need to exceed the osmotic pressure of that water in order to create that flux of water across that membrane surface. So let's look at a situation. We have a salt water concentration of 35,000 milligrams per liter. This is typical for seawater. We'll assume that for every mole of seawater, so for every mole, for instance, of sodium chloride, we will produce sodium plus chloride. So for every 1 mole here, we produce a total of 2 moles of ions. The osmotic coefficient for sodium chloride is 0.85. We'll assume we have a C temperature of 15 degrees C, and we'll use the molecular weight of sodium chloride. So you're asked to calculate the osmotic pressure. The way we do this, we're using the ideal. We take pressure, divide both sides by volume. We have concentration, it's RT. The notation we use for osmotic pressure is pi for osmotic pressure, and that's equal to I times the osmotic coefficient, I is the number of moles, times the concentration times RT. So we're replacing N over V is just our concentration, and we have I and phi to represent the osmotic pressure and the number of moles. So again, so we've used NaCl. We said we've got 35,000 milligrams per liter, and that dissociates to form sodium ions plus chloride. So I is equal to 2. So then the osmotic pressure is 2 times the osmotic coefficient times the concentration, and we'll multiply, divide that by the molecular weight. So milligrams cancel. We'll now multiply, we have millimoles. So we have 10 to the minus 3 moles per millimole. So millimoles cancel. And we'll multiply that by 0.082 atmospheres, liters, moles. And we still need to multiply by the temperature, and the temperature needs to be in Kelvin. Temperature cancels, moles cancel, liters cancel, and we have our answer in atmospheres. So the osmotic pressure is 24 atmospheres, or about 350 psi. So we need to exceed that in order for the water to actually pass across this membrane. If we raise the temperature, what happens to the osmotic pressure?
Is it going to go up?
It's going to go up. Okay. It's linearly dependent on temperature. If we raise the concentration, what happens to the pressure?
Go up.
It's also going to increase. Okay, so higher the concentration. So you can see if we were looking at wastewater reuse, where our salinity is typically, think of it around 1,000 milligrams per liter, the pressure you need is significantly less than what you need for seawater. Now, the flux of water across the membrane can be described by this equation here. So the flux, notice here, is either in kilomoles per second per area. So this is the area of the membrane, really a specific flux. And here we have it as a volumetric. So it can either be as mass per second or it can be as volume per second. And it's dependent on this coefficient of water permeation, which is dependent on the membrane. And notice here, this is dependent also, it's your flow divided by the surface area of the membrane times the pressure. So it's a specific coefficient, really. It's, since we've included pressure, dependent on the pressure. And it's, that flux is dependent on what we refer to as the transmembrane pressure. That's the pressure difference across the membrane surface. This is transmembrane pressure. And this is the difference in the osmotic pressure in the across the membrane surface. So we're both looking at across the membrane surface. This is the pressure, the transmembrane pressure. So it's difference in the pressure across that membrane. And this is the difference in the osmotic pressure between your feed solution and the permeate. The solute flux is the flux of salt or other chemicals that pass across the membrane surface. So for instance, if we're looking at that sodium chloride solution and we have a membrane surface, so here's our membrane, we'll take seawater, we produce a product stream and a reject. That product stream will have some salt in it. Perhaps we have 99, what we refer to as 99% rejection. That means if we start at 35,000 milligrams per liter, how much salt is in the product water?
1% of that.
1% of that. So 350 milligrams per liter of salt, or sodium chloride. So some of the salt will pass across that membrane. It's not 100% removal. And what this equation here shows you, one, it's dependent on the difference in concentration across that membrane surface. It's also a function of the membrane itself. So different membranes will have different mass transfer coefficients or different removals of your salts. Now, it's dependent on the diffusivity, which describes the rate of diffusion of that chemical. The higher the molecular weight, the lower the diffusivity. The chemical is not going to diffuse either in air or water as rapidly if it's a higher molecular weight. As temperature increases, the rate of diffusivity increases. So if this is true, as molecular weight increases, diffusivity decreases, and how does the flux of salt change? If we're looking at salts having a higher molecular weight, so for instance, we could look at chloride, we can look at bromide. Which one has the highest molecular weight?
The bromide.
The bromide. Okay. So if that has the highest molecular weight, diffusivity decreases. So how does the flux change?
Would it decrease?
It'll decrease because it's proportional. So your flux is proportional to the diffusivity. On the other hand, if the temperature increases, so if we just look at chloride, as the temperature increases, diffusivity increases. So now what happens to the flux for that same salt? So if temperature increases, as temperature increases, my diffusivity increases, what happens to the flux? Exactly. Okay, the flux will increase. Which means what? Why is this important?
Would we want to run the desalination plant at a colder temperature?
Exactly. So, or for instance, if you're looking at wastewater, during the summer when the temperature is higher, you'll have more salt in your permeate stream because the diffusivity is greater. It also means that in terms of designing, you need to design, if you want a certain removal, you need to design for the highest temperature. You'll get better removal in winter, but that's your controlling temperature. That's your controlling situation, is the high temperature. So you design for the high temperature in terms of the solute flux, and then you have better removal in winter. We also talk about recovery. When we talk about recovery, we're talking about the water. So for instance, we have a water stream and we have a pump, and then that water flows, passes through a membrane. A certain portion of it will be our product stream, and a certain portion of is the reject stream. So in this case, let's say we produce 75%. So that means 75% of the feed is product water or permeate. 25% of that flow is reject stream. And this we have to dispose of. We'll talk about disposal on Wednesday. When we talk about rejection, we're talking about the salt. And I mentioned that before when I said 99% rejection. So there we're looking, as I mentioned, with feed. So let's say we start at 35,000 milligrams per liter. If we have 99% rejection, we have 350 milligrams per liter in our product water. Now, the other terminology that's used is this terminology about arrays. So we have feed water. We have product water that we're producing. So this is our product water here. We have our reject stream. And what we're doing here is we're taking that reject stream and we're passing that through a second membrane system. Again, we have a reject stream here, and we have a product stream here. This is referred to as a 2-by-1 array. So we have 2 stages here, followed by 1 stage here. Why would we do this?
We make the first stage like a larger pore size, and then the second stage a smaller pore size.
We could do that. So we could change the pore size. Okay, we also, typically your stage 1 is going to have more membrane units on it. So you're basically squeezing out as much water as you can reasonably do for this type of a situation, okay, for that conditioned water. And then what you're going to do is you're going to take the reject stream. You'll have a smaller membrane unit there, and you're going to try and essentially squeeze out more water. So you're basically trying to produce as much water as you possibly can from that feed stream. This is an example of a system in Sydney. I'm only going to play a portion of the video.
The St Mary's Water Recycling Plant uses reverse osmosis to further treat wastewater after the ultrafiltration process. Reverse osmosis membranes are constructed from a membrane flat sheet. It is comprised of 3 layers: a polyester fabric support base, a microporous polysulfone layer, and a 0.2 micron thick polyamide barrier layer. The polysulfone layer strengthens the very thin barrier layer. It is the barrier layer that removes nutrients, chemicals, bacteria, and viruses from the water. The membrane flat sheet is combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets for the feed water. A sheet of permeate spacer is added to the membrane sheets and feed channel spacer. This enables the final recycled water product, or permeate, to flow evenly across the entire membrane surface, even under high pressure. The back of the membrane is completely sealed to the edges of the permeate spacer. The membrane sheets are glued along each of the 3 exposed sides and rolled around the core tube. Feed water is forced through the feed channel spacer and into the barrier layer of the membrane. Water passes through the membrane surface into the permeate channel. It flows in a spiral direction and collects in the core tube. This water is the final recycled water product, or permeate. There are 7 spiral wound elements loaded in one pressure vessel. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced. Feed water is pumped at high pressure into the vessel. As it travels, small molecules like water pass through the membrane, while larger particles such as salt, bacteria, and viruses do not. The final recycled water product is collected from the end of the elements. The concentrate or reject from that vessel flows to another stage, producing more recycled water. At St Mary's, there are 6 reverse osmosis treatment trains, each with 3 stages. This design produces the highest amount of recycled water with reduced concentrate waste. Stage 1 has 52 pressure vessels, Stage 2 has 24 pressure vessels, and Stage 3 has 12 pressure vessels. 58 million litres of feed water enters the reverse osmosis system on a daily basis. As the feed water passes through each stage, more recycled water is extracted. 65% of recycled water is extracted at Stage 1. The remaining 35% is passed through Stage 2, where a further 10% is extracted. The final 25% is passed through Stage 3, where the last 5% of recycled water is extracted. 80% of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St Mary's. The remaining concentrate contains so much salt and impurities that to recycle it would not make economic sense. This concentrate stream of 8 million litres a day is sent to North Head Wastewater Treatment Plant, where it is treated and released into the ocean.
We'll end there, but I just wanted you to have a sense of what a treatment system really looks like. Notice here, they've used 3 stages to try and achieve as much product water as they possibly can. And notice the number of units. So they've got 52 in the first with 6 in each, 6 membrane elements in each of these vessels in order to produce the requisite amount of water. So we'll end there. And I apologize for going a few minutes over. And then we'll pick up with the rest of membrane treatment on Wednesday. Thank you and have a great day.